A current modern technique for designing controllers in practice is referred to as internal model control, or IMC. And what I'll do in this video is provide an introduction as to how engineers in practice are able to design IMC-based controllers. And to do that, we will be working with transfer or control block diagrams that look like this. And so we'll have this transfer function g tilde here, which will represent our internal model of a process. And this will be an ideal model that is perfect. And as we know, the real world is not perfect. There are disturbances that we need to take into account. And G here would be the actual physical model of our process, which is very difficult to actually compute. And so what we'll do is first we're going to transform this control block diagram of IMC into something that more closely resembles the standardized control block diagram we're used to in closed loop transfer functions. And to do that, we rewrite our block diagram as this. So we'll still have some kind of demanded set point YSP, and we'll have an error present. And this error will enter into some kind of control block that we will make a little bit different. And we will have, if we implement a control block diagram and modify the above diagram, what we would see is that we can rewrite this as g tilde, our internal model, and our internal model controller function q. And this is what's actually going into our process G. And so rewriting it like this, including our disturbance and our output, as well as the feedback, we can now recognize that we can define this inner loop here as an additional transfer function, which we refer to as GC. And so GC is equivalent to Q divided by 1 minus Q times G tilde, our internal model. And so if, as we've done previously in videos, typically this is kind of like a pseudo characteristic equation. We have a minus sign here, which is different from the typical plus sign that we have, and this is because we are adding the feedback back into our loop, because if we look here, we've got essentially a double negative, and so we need to take that into account. And so what we end up with is that GC, the controller function that we're going to want to design for this process, will have this form. And so we are interested in PID controller design, and so we can rewrite this in the form GC is equal to the quantity tau I, the integral time constant, times the derivative time constant tau D times s squared plus tau IS plus 1 divided by tau IS, and we will multiply this function by, I'm sorry for going off the page here, but we multiply this by a filter to make this a physically realizable system, tau FS plus 1. And the reason we need to do this is because we'll note in this first term how the degree of the numerator is 2 and the degree of our denominator is 1, and to be a physical process, the degree of the denominator must be greater than or equal to that of the numerator. And so in that case, we need this filter term here to take that into account and make things work out. And so what I'll do next is work through an example of using internal model control to design a PID controller for various process types, such as a first order process without dead time and a first order process with dead time, and so on. And so this kind of wraps up the general introduction to IMC. I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.